Hi, in the previous video we learned about the centripetal accelerations formula as well as the definition of linear velocity and angular velocity. So with the equation, I'm pretty sure that you can already do a few questions. So let me ask you to do these questions 6.1, 6.2 and 6.3 for now. So please pause the video and try yourself and I will show you how I would do it. Example number 1. Given that the Earth orbit has this radius, calculate the angular speed of the Earth rotating around the Sun and also the linear speed in the part 2. So let's do angular speed first. So remember angular speed, we are trying to find out the answer in the unit of radian per second, and for linear it will be meter per second. So the idea is very simple. You just have to use your common knowledge that when the Earth is revolving around the Sun, it takes a year. Okay, so that will be 365 days. That's a number that you simply have to remember, which again is got common sense. So for angular speed, then obviously that will be 2 pi, because or maybe I should quote the equation, omega equals to 2 pi over t, and that will be 2 pi over 365 days, 24 hours, 60 minutes, 60 seconds. Again, remember our answer is in radian per second, not per day. So by using your calculator, you should be able to find something like 1.992384 something times 10 to the power of -7. So I will run this to, well, I think 268. So 2.0, 10 -7. Again, you have to write down the unit, radian per second. As for part B, R omega equals to V. If you don't remember, you can go back to the data booklet, which is right here, right? Something you can recall, or you can just simply think from the definition itself. So that is to say, the V will simply be, or maybe I can present better if I write this way, and so simply is the answer, or I can use the whole number if possible, times the radius, which is already in meter, so it's good, and using your calculator it shall be 2.98 something. So let's take it as 3.0 times 10 to the power of 4, and this is in meter per second. So in fact, if you try to make sense of this, then maybe we can change it to 3.0 times 10 to the power of 1 km per second. This is a very interesting question because think about this, think about the linear speed of the Earth. We are moving with the Earth around the Sun, and we all are moving in such a speed. Can you imagine you are moving 30 km per second right now when you are watching this video? So 30 km, 60 km, 90 km already in these 3 seconds. And so that is to say, if somehow the Earth, while it's moving, somehow the Earth disappear. Okay, so you still are in the universe, but then the Earth somehow suddenly disappear, or somehow the Earth stop moving, but you still have the inertia to be moving forward. So what happened is, imagine in this diagram that the Earth would be stopped, or it would simply vanish or disappear, but then what happened to you will be you'll be moving to the nowhere of the universe with such a speed, so 30 km per second. But of course, this disregarded the self-rotation of the Earth. So if you want to find that out as well, you can calculate it with a similar approach. Let's talk about the next example. So here it just asks you to calculate the centripetal acceleration. You have got the radius, you have got the angular speed. By the way, for all the circular motion that we talk about in this chapter, they are all having a constant circular motion. So that is to say, the acceleration is always a constant. If acceleration is changing, that will be way complicated, and we don't cover in this topic. So yeah, I mean that's something you need to realize first. So anyway, these are all the information that we have, and we have to think about the equation for calculating centripetal force simply. So we have R and omega. So let's just go back to take a look of the equations that we have, 1, 2, 3, 4. So the one that you should be using should be 3 omega square R. Again, I will try to write omega like this, right? Try to distinguish between W and omega. Omega R, omega square R. And so just substitute, make sure they are in the SI unit. So radian per second is good. This one in meter is good. And so just use your calculator. Alright, the answer would simply be 8.82, but then because of the sig fig, I'll take it as 8.8 only, and the answer should be in meter per second square. So if you want to, you can use that as well. Of course, you may say, hey, if I try to deduce from this equation, then what will you get? I'll give you 10 seconds to think about it. Alright, let's just work out together. So the units of A could be, using the equation, radian square as -2 with omega square and meter. And so if you somehow rearrange it better, that will be meter per second square with radian square. So in fact, if you try to compare it, you'll find out, hey, isn't this the same as meter per second square already? So does that actually means radian square is actually dimensionless? The answer is actually yes, because normally in mathematics you don't actually write the word radian. Alright, it's a concept to help you to understand when we write the word RAD, radian, but then in fact you can express it as 2.1 per second, like that, right? For example, for this one. But then for a clearer presentation, then we'll also put down radian. So in fact, some people may just like to hide it because it's not really a dimension. It's just a way that will work with the number system that we have instead of using the degree system. So yeah, it's the same thing. So the unit is still meter per second square. Next example. So we are talking about Earth here, and imagine you are on the equator. This is the equator, and you have got the radius. It asks you to determine the centripetal acceleration, so finding out A once again. So obviously you need to know more information to calculate this. So other than R, one more thing that you should know is by the spinning of the Earth, that means the self-rotation, then T would equal to 1 day. So that is 24 hours times 60 minutes times 60 seconds. So if you simply use this to find out any equation that is related to R and T, and that's going to be equation number 2 right here. So 4 pi square R over T square. So we just have to write down the equation once again and substitute the information that is given from the question. So 6.4 times 10 to the power of 6, and also the T. Please don't forget to take the square and then use your calculator. The answer that you find is something like 0.0338. Okay, like this one. And so we can express the answer with 2 sig figs, so that is 0. Well, actually we can do, I think this one is pretty good already, but anyway, 3.3 10 to the power of -2 meter per second square. So you may be wondering, what does that actually mean? That's the exact question I want to ask you, so give you 10 seconds. First of all, I have to say, when I was a student, I also did a similar question like this one. And after I understood everything, and my mind was like blown once again by the physics. And in fact, this number is actually very, very meaningful. So let me explain to you, and hopefully you also have the mind-blown moment later on. If you don't, then probably you don't understand. Let me explain to you. So this is centripetal acceleration, and this is very small. And so you may be wondering, hey, shouldn't acceleration to be 9.81 on Earth? But then here, we are talking about the circular motion, so don't mix them up. The gravitational acceleration is still about 9.8 something, but then here is another idea. So imagine this, when you perform the circular motion, you still follow the Newton's law, which is F equals to ma. So here we have the force to be centripetal force and the A to be centripetal acceleration. However, if you think about the free body diagram, okay, and let's say you are on a balance, okay, electronic balance, like out of nowhere, right? Like the previous topic when we learned about mechanics, right? There's always a balance in a physics equation, isn't it? So we will have two forces, which is weight and also the reaction force. However, in this case, because we are moving in a circle, there must be a net force acting on our body, non-zero net force, which acts as the centripetal force. And that is to say, if you by looking at the direction of weight and reaction force, the only possible way to have it is to have the weight to be bigger than the R, and therefore you can have a non-zero net force. So here we will put it as W minus R equals to MAC first. All right, let's keep it like this first. And so let's think about a situation where, let's say I'm 70 kg, and so for the weight, if I simply use the 9.81, then we can have 70 times 9.81 to be 686.7 minus the R. R is the unknown, which is the reading of the electronic balance, and M is 70, and here is the A, 0.038338, sorry. And so if you solve this equation, then you would have the answer minus 70, 0.338. So you will be able to find your R to be 684.334 Newton, which means it is smaller. So that is to say, if you somehow have an electronic balance, and if you step on it to measure, it will be less than your actual mass, because when you think about the actual reading, okay, if I convert it back to kg by dividing it with 9.81, then you get 69.75 kg, right? While originally I was saying I was supposed to be exact 70 kg, and now you have slightly less mass according to the electronic balance. Of course, you didn't really lose the mass, right? You still have the same amount of mass there, but there is an illusion where, because you have to spend that tiny part of the weight to support this circular motion, then the reaction force that you need will be less, right, to support from the ground. So this is an interesting thing that I find when I read this, and I mean doing all this calculation, and this is really mind-blowing. And if you think about, then what about the other position of the Earth then? Then you have to calculate the exact, how much angle together with the rotational axis. Let me take it very extreme, and that is at the North Pole, for example. So at the pole, and since in theory, if you are exactly at the pole of rotation, of course, then you are not basically you're not rotating at all, right? If you are on the axis. So in that case, then nothing will happen. I mean that would simply be reading how it should be, right? And so the electronic balance should read 70 kg exactly. So this is the interesting fact that we find out because of the rotation of the Earth. if you're measuring your mass at the equator, it will be slightly less. If you're interested to know how does the different positions around the Earth will have a different effect of the apparent gravity, like what we said, in the equator it will be the maximum, at the pole it will be 0 literally. So how about the other position? That would depend on the angle. And if you want to know more about how to derive it and what's the reason behind, I'll recommend you to go to this website and follow and read through these things. So I'll put a link in the description below. Alright, so for now I would like to push for 2 more questions before I end this video. So please do 6.4 and 6.5. Pause the video, try it yourself, and I'll show you the answers.
A few moments later.
So 6.4 is not really a classic question like, you know, this is like literally the classic question in 6.3, but then this one is still a pretty interesting question to think about. So what it said is if you're moving from A to B in a circle with constant speed, and it asks you to find the direction of velocity change. So obviously what you have to do simply is just to draw the vector. So this is VA, this is VB, and again if you want to find the change of velocity, then that will be the nu minus the O. So in this case, then we should have the negative VA to be going down, and so if you try to put them together, then I suppose they would be going in such a direction. Okay, and so this is the direction that you have, but then you may be wondering, right, so what does that actually mean? Think about this. When you are moving from A to B, then this vector actually I should draw from maybe the midpoint of the path between A and B. So this is supposed to be delta V, but then I think ideally I should put it like here, right, for delta V. So this to show you how does, you know, the A equals to delta V over delta T is being defined, and again the direction will still match. Let me give you a bonus part. So what if I say this is C and the delta V when you move from B to C?
A few moments later.
And the answer will be pretty much the same, because at C then you'll be having VC going here, and once again if you want to find the delta V from B to C, then that will be the nu minus the O, and so in that case you will be having VB negative going to the right as well. And so eventually if you look at these two vectors, VC and negative VB, when you add these two together, it must be a vector that is going to the right as well. And across B to C in this arc, then the kind of midpoint is right at here as well. So then the delta V will be right here as well. So the direction will still match. Okay, last question. If you don't know how to do this completely, feel free to pause at any time of this video and try to give yourself a try. Okay, so let me give you some hint. Here we've got coefficient of static friction, so something to do with friction obviously. This, let's put down the symbol, is mu. This is m. We have to find out maximum speed, so let's call it v max is something that we want to find, and the radius is r. So in order to understand this, then you have to imagine the car is using the friction to make a turn, just like what we said in part 1 video. And so we just have to apply the Newton's second law, F equals to ma in the circular motion. So centripetal force, centripetal acceleration. Here, the centripetal force that you have is simply friction. So let me just put down a lowercase f here. M is something that we can substitute later on, and for A, you can go and check the equation that we need, and this would simply be v squared over r. Okay, and 27.568 something and so we could run it to 2 so 28 meter per second. Okay, so this is under the circumstances of that much of coefficient of friction, and also that much of speed and that much of radius. Yeah, that will be the configuration for part A. Part B, however, okay, is also quite interesting. It says now the road condition become wet, and so the coefficient of friction will be reduced because it's slippery, right? So then it becomes half of the original. So that is to say the new mu becomes 0.40 right now. So can you predict the safe maximum speed? So when we say safe, that is to say the friction is enough for you to make a turn. Again, refer to what I said in part 1 video. If you don't have enough friction, what happens to your car is you are going to move forward if you have no friction, or if you have not sufficient friction, then the only way that you can compromise is you will somehow make the circle become bigger. Okay, think about like the equation itself. Alright, if you don't have sufficient force, friction, then the only way that you can compromise with the same v, because v probably is the speed you're already traveling, then you can only make the L bigger, and that should say you cannot turn as steep. However, this is not the same question in part B. Part B is asking you the new maximum speed. So it's actually quite simple. You can actually use what we have earlier. Then so I'm not going to repeat over again. So you can just write mu g equal to v max, the new v of course, over r. So this time we have 0.4, and by the way, if you think the speed would simply be divided by 2, then obviously you're wrong, because here you can already see there's a square, so probably is something to do with the square root. So 10, and this is a new Vmax, and R is still 95. So once again, if you use your calculator, then you find the new Vmax to be 19.49 something. So let's run it to 2 so 20, not 20, actually 19 only meter per second. So you can see it's not exactly half, because half is like 14. So now you got 19. So here we have it. We have finished 5 examples of circular motion questions using the equation that we learned in the previous video. Let me make a small summary here. The main idea of doing all these questions is nothing more than just recalling the equation and substitute the numbers into it. One of the challenging part is you have to select the corresponding centripetal acceleration formula in order to calculate efficiently. The other thing that you may find challenging is probably question 3, where you have to understand how to apply F equals to ma. But I would say for the rest of the question, it should be quite simple for you. And so in the next video, we'll start to do something that is slightly more complicated, because we will be talking about some example like a vertical circular motion that has more consideration than what we did. It could also be a 2D motion. So as you can see, there's a horizontal circular motion, but at the same time you have to consider the vertical forces as well. I hope you enjoy learning physics with me. If you do so, please hit the like button and subscribe to my channel. I'll see you again in the next video. Bye.